We have these AI models now that are just incredibly powerful. They can solve all sorts of complex problems, but there's a catch. Sometimes they just don't know when to quit. So today, we're going to dive into a really cool idea. How do you teach an AI the crucial skill of knowing when to just stop thinking? So let me just ask you straight up. Do AI models overthink? It sounds like such a human problem, right? But it turns out the answer is a big, resounding yes. And just like with us, it can lead to a whole lot of wasted time, energy, and in the world of AI, that means a lot of computing power and money down the drain. So here's the problem. When you give a large language model a really tough reasoning task, it can get stuck. It just goes around and around in these long, unproductive loops, generating thousands of extra words, or what we call tokens. All this unnecessary thinking just chews up massive amounts of computing power, which makes these amazing tools way less efficient and a lot more expensive to actually run. Okay, so here's our game plan for today. First, we'll really dig into what we mean by the overthinking problem. Then we're going to peek under the hood and look at the anatomy of an AI thought. After that, I'll introduce you to a really clever solution called CodeStop. We'll see how it did when they put it to the test. And finally, we'll talk about what this all means for building a future with smarter, faster AI. All right, let's get right into it. What is actually happening when an AI just can't stop thinking? It's not just about being slow. Sometimes all that extra thinking can actually make the final answer even worse. Researchers figured out that AI reasoning paths pretty much fall into two buckets. On one side, you've got what we can call correct thinking. This is the ideal path. The model finds a direct, stable way to get to the right answer, it gets super confident, fast, and then it stops. Simple. But then you have incorrect thinking. And this is where the model gets lost. Its reasoning is all over the place, its confidence goes up and down, and it gets trapped in these loops that can literally make the process twice as long, doubling the cost, and it might not even get the right answer in the end. And wow, this slide illustrates that difference perfectly. Let's really take a close look at these graphs because they're fascinating. So on each plot, the vertical axis shows the AI's confidence from 0 to 100%. The horizontal axis is the reasoning step, which is basically just how long it's been thinking. Now look at those blue lines on the left. These are all the times the AI got the answer right. See that pattern? They all shoot up to a really high confidence level, close to 1, and then they just stay there, flat, steady. It's found the answer and it knows it. Okay, now look at the orange lines on the right. These are all the times it got the answer wrong. It is pure chaos. The confidence just bounces all over. It jumps up, it crashes down, it wavers. It never settles into that stable, high confidence state. This right here is the visual signature of an AI that is totally lost and overthinking. So seeing this huge visual difference between the correct and incorrect paths, that was the key. It made the researchers think, okay, we need to look deeper. We need to analyze the anatomy of an AI thought, not just where its confidence ends up, but the whole dynamic of how it changes over time. Now this is where it gets really, really cool. Look at these two graphs. On the left, you see the average confidence for all the correct paths in blue and all the incorrect ones in orange. And check this out. The biggest difference between blue and orange is right at the beginning, in those first few reasoning steps. As the AI thinks longer, both lines actually trend up, and they start to get all mixed up. That means the model can get more confident even when it's wrong, which makes it hard to tell if it's on the right track later on. So that led to the genius idea on the right. The researchers came up with something they call a degeneration score. Just think of it like a penalty. The score goes up every time the AI's confidence wobbles or dips. And look at that result. The separation is now crystal clear. The score for the wrong paths, that orange line, it just keeps climbing and climbing. Meanwhile, the score for the correct paths, the blue line, stays flat and super low. It's a perfect signal that the model is spinning its wheels. So what this all boils down to is a really powerful insight. It's not enough to just ask an AI, hey, how confident are you right now? The real secret, the real signal, is in the journey. By looking at how that confidence changes, its dynamics, we get a much, much clearer picture of whether it's actually making progress or just going in circles. And this big idea is the foundation for a brilliantly simple and super effective solution, which the researchers have named CodeStop. CodeStop stands for Confidence Dynamics Early Stop. Now, the absolute best part about this whole thing, it's a training-free method. That means you don't have to go through the incredibly expensive and time-consuming process of retraining these giant models. You can just plug this method into existing AI systems and boom, they're instantly smarter and more efficient. It just watches the AI's confidence behavior and uses that to know when it's time to pull the plug. And how it works is really a simple two-part strategy. First, it does the obvious thing. It checks if the model is really, really confident in its answer. If the confidence is high and stable, great, stop thinking. We've got our answer. That takes care of all those good direct thinking paths. But the second part, this is the really clever bit. It uses that degeneration score we just talked about to spot unproductive thinking. So if the model's confidence is all shaky or just isn't getting any better, CodeStop recognizes, hey, this thing is probably stuck, and it tells it to stop right there before it wastes any more time or money. Okay, that all sounds great in theory, right? A simple plug-and-play solution, but the real question is, does it actually work in the real world? Well, the researchers put CodeStop head-to-head against a whole bunch of other methods to find out. All right, let's break down this graph because it tells the whole story. On the vertical y-axis, we have accuracy, so higher is better. On the horizontal x-axis, we have the computational cost, so lower is better. That means the perfect place to be on this chart is the top left corner, maximum accuracy for the minimum cost. Now, each of these colored shapes is a different method trying to solve this problem. Go ahead and find the yellow star. That's CodeStop. See how in both charts it's consistently hanging out closer to that top left sweet spot? It's hitting an accuracy that's right up there with the very best methods, but it's doing it for way, way less computational cost. It's just a clear win on efficiency without giving up any performance. So what does that amazing top left performance actually translate to in real numbers? Well, we're talking about a massive reduction in the total number of tokens the AI has to use. A reduction of 25 to 50%. I mean, let that sink in for a second. That's like cutting the time and the cost of running these huge, complex reasoning tasks by up to half. And the crucial part is, it does this without hurting the model's accuracy one bit. It's a huge, huge leap in efficiency. So, let's zoom out. Making an AI more efficient isn't just some neat academic trick. This has real-world consequences for how all of us can use these incredible tools. Look, here's the bottom line. By teaching an AI a little bit of self-control, by teaching it when to stop, we make our most advanced models way faster and way cheaper to run. This lowers the barrier to entry, which makes this kind of powerful AI reasoning more accessible for everybody, for researchers, for small companies, for students, which is just going to accelerate innovation across the board. And that kind of leaves us with one final thought to chew on. If we can basically make our most powerful thinking tools twice as fast and half the price, what new problems could we solve? What new inventions or applications suddenly become possible? It's a pretty exciting future to think about. Thanks for joining me.